is Engr, Eternal Voice. So welcome to my Chemical Engineering Diary, July 8, 2021. Okay, so let's continue about the law of thermodynamics, second law of thermodynamics. But at this point in time, we are not having the problem solving yet. We will just discuss to you the theories, concepts, and principles behind the second law of thermodynamics. Okay, and I will be able to show to you the basic equation, basic formula, basic concepts, and then the correlations for each formula, something like that. Okay, let's start now. Okay, now in the second law of thermodynamics, we are introducing, I think, three terms. Three terms. Yeah, it's gonna be the enthalpy, the entropy, and the Gibbs free energy. Okay, and now let's define each. Okay, what is Gibbs free energy? Gibbs free energy is determines the spontaneity of the process, how spontaneous, how non-spontaneous really the process is. So the sign plus and minus is very important here. Okay, now second, the enthalpy. The enthalpy is the heat content, okay? Meaning to say the energy heat transferred from one point to another point. The heat energy releases or occurs to the environment from the system to the surrounding. We mean of surrounding, it's basically the environment. Okay, so there's a heat energy transferred from high temperature to lower temperature. Okay, that's enthalpy. Okay, it's basically the same with heat, but heat is simply as heat. Okay, meaning to say no need to be transferred from one point to another. It's just heat alone. Okay, but for enthalpy, it should be having the reference points from A to B, from system to surrounding, like that, and heat energy is being transferred. Okay, do not be confused with the terminologies. Heat is being transferred, heat is being released, heat occurs, heat absorbed, heat removed, heat added, like that. But always think of this, guys, that we need to consider as a reference is the system, okay, not the surrounding. Okay, the sign also depends also with the heat Q will be just the same as the enthalpy. The sign, could it be positive heat or positive enthalpy, negative heat or negative enthalpy, something like that. Okay, so this might be having the same concept. Okay, this enthalpy and the heat, and then the last will be the entropy. Okay, so entropy has the formula of, okay, heat in the numerator over the time. This is entropy. Okay, so I have to show the formula now. H for the Gibbs free energy, like this. This is the Gibbs free energy. So we have the enthalpy, change in enthalpy, minus, okay, temperature times delta S. So this is specifically the second law of thermodynamics. Okay, where did we get this change in temperature? No, change of entropy and the temperature. This is from Q over T. Okay, this is Q over T. So Q over T is simply the entropy. Okay, so delta S is equals to Q over T. So we need to say this heat here is the capital Q here. So we have the uh, change in delta G, Gibbs free energy equals to enthalpy minus the heat. Then cross multiply delta S entropy times the temperature, something like that. Okay, now class, this is at reversible reaction. So let's say R like this. So if we treat this in a reversible reaction, so our entropy will be equal to 0. The change in entropy is equal to 0. Like this, at a reversible reaction. So therefore, there's no quantity here anymore. So we can say delta change in energy is equal to the enthalpy alone. Okay, something like that. So if this is an irreversible reaction or irreversible process, then we are not considering the entropy is equal to 0. Okay, so we need to have greater or positive value of the entropy, and this is the second law. The sum of all entropies in the system of the surrounding is always increasing, or the entropy in the universe, okay, entropy in the universe is equal to the entropy in the system plus the entropy of the surrounding. This one. So meaning to say, the entropy of the universe is always increasing. Okay, like that. So it is a randomness and disorderedness of the universe. Okay, like that's equals to the entropy of the system plus entropy of the surrounding. If we treat entropy of the surrounding is this at reversible reaction, so we can say directly entropy of the surrounding is equal to the entropy of the system. If we treat this part here as reversible process in which entropy is equal to 0, or treating the entropy as constant. Okay, the more reversible is our process, the more we treat our entropy constant and 0. So the more irreversible the process really is, or irreversible the chemical reaction, then we need to have an increasing entropy. Okay, again, the more we have an irreversible chemical reaction or irreversible process, the more we have an increasing entropy. The more we have a constant entropy or 0 entropy at equilibrium, meaning to say, the more it is a reversible chemical reaction or reversible process. So reversibility of the process depends on the value of the entropy. Okay, so most of the chemical reactions or process are irreversible because it is impossible to have the ideal or perfect, okay, process or chemical reaction. Okay, for example, to this is the Carnot cycle or the heat engine, okay, which discovered by Sadi Carnot. Okay, so he said, he postulated that the heat to be converted to work, it's impossible to have a 100% of efficiency. Or we can say like that, no cyclic process, okay, if our efficiency is 100%. Okay, in a cyclic process, the efficiency is always less than 100%. That is his postulates. That's why we can base that to the formula efficiency is equals to work done by the heat engine over the heat absorbed or heat input of the heat engine. And specifically, heat engine is an example of the second law of thermodynamics, which is discovered and postulated by Sadi Carnot. Okay? Carnot, C-A-R-N-O-T. So we have Carnot cycle, cyclic process, right? So if I will illustrate that one, heat engine is second law of thermodynamics. We have, for example, we have the here the temperature input, and then let's go here Okay, temperature output. Okay, okay, and then we have also QH here and QC here. So this is an illustration of the heat engine under cyclic process. So this obeys second law of thermodynamics. Okay, like that. So trading internal energy is equals to Q. So meaning to say work is equals to the heat absorbed minus the heat released. The heat absorbed, okay, of the system or of the heat engine minus the heat released or transferred to the environment, or of course to the environment. That's why we have work is equals to QH minus QC. H represents the system or the heat engine itself, and then C represents the environment or the surrounding where the heat is being transferred. Okay, so we have here work is equals to QH QC, or we can say also work is equals to TH TC, like this. We can use this work because of the temperature input minus temperature output, right? Like this. And the heat absorbed or heat input minus the heat released to the surrounding, to the environment. Okay, here in the second quantity is always to the surrounding, to the environment. Here is always from the system or from the heat engine. Okay, the same story. So this comes from the formula of Q is equals to unstability, wherein treating mass and specific heat as constant, or there's no change in specific heat capacity and the mass. That's why you will say heat Q is equals to the change in temperature only, like this here. This is only the change in temperature absorbed, release, or input and output. Since change in internal energy is equals to 0, then Q is equals to W. Okay, like that. So that's what we have here. So we can also denote this also as Q, but Q is equals to work. That would be fine to use another symbol or letter like that. Okay, so like that, very easy, right? And then we have also the Q is equals to the T times the entropy here. Okay, so in the second law of thermodynamics, the introduction of the Gibbs free energy, the entropy are very common. Not very common, but shall we say very important. Okay, and then in the first law, there's an introduction of heat, work, and internal energy already, but the heat there can be also treated as an enthalpy, because enthalpy is the heat content, heat energy transfer, and then heat is also heat energy. Okay, whether it is transferred or not, it is heat. Okay, driven by temperature changes from high temperature to low temperature, from cold temperature to low temperature, something like that. Okay, that's very clear. Okay, now we go to the concepts and theories of Gibbs free energy. Okay, first, right? Okay, we go there. Wait, let's check the time. Okay, we have still time to discuss. And then we go to the relationship now. Okay, relationship. So we have Gibbs free energy. If equals to negative, this is spontaneous. If the Gibbs free energy is equals to negative, this is spontaneous reaction. Okay, like that. Okay, and then if the Gibbs free energy or delta G is positive, this is non-spontaneous. This one. So in the first, we can rewrite this as if delta G is less than 0, the negative spontaneous. Gives free energy is less than 0, spontaneous. Now the reverse will be if delta G gives free energy is greater than 0, so it has a positive sign or non-spontaneous. Okay, like that. Then class, in the second law of thermodynamics also, the change in enthalpy H will be regarded also the internal energy. Okay, so how can you say that? Because we treat the work will be equal to 0 at this point in time. If the work will be equal to 0 from the first law of thermodynamics, delta U is equals to Q minus W in the first law of thermodynamics, right? So delta U will be just equal to Q. Since Q is just equal to enthalpy, that's why we need to interchange the enthalpy to delta U also. I will show you, okay? From the first law of thermodynamics, sa ganito, sa first law of thermodynamics, energy can neither be created, okay, nor can be destroyed, but it can only be transformed into various types of energies or governed by law of conservation of energy. This is the first law, and we have the delta U is equals to the heat minus the work. This one is the first law. Okay, this is the first law. Since then we assume that this is an isovolumetric or isochoric thermodynamic process in which there's no change in volume. Okay, and from the equation, work is equals to pressure. There's the change in volume, so this must be 0. So work is equals to 0. If we treat this an isochoric or isovolumetric thermodynamic process in which there's no change in volume, so automatically our work is equal to 0. If we substitute work is equal to 0 here, therefore delta U is equals to Q. Okay, remember delta U is equals to Q, change in internal energy is equals to Q. Q is also a heat energy content. So we can also say that this is also an enthalpy. So delta U is just equals to the delta H, because the Q is also heat, okay, energy, and the delta H is also the heat energy or the total heat content, something like that, transferred like this. So this will be equal now already. So if we have the general equation of the second law of thermodynamics, which is this, right? So delta G is equals to second law, which is change in enthalpy minus T times entropy. So we can also say that delta G is equals to, okay, like this, delta U minus T delta S. So this is just equal your equations here. So delta U is equals to, okay, enthalpy minus temperature times change in entropy, okay, and then it is also equal to, okay, this one gives free energy change, and gives free energy is equals to the delta U minus d delta S, because of this principle here, or treating this as an isochoric or isovolumetric thermodynamic process, something like that. Okay, so that's why some books or some reference textbooks, you can find one of this, and this involving internal energy usually applied in the subject purely in thermodynamics, and this also can be applied purely most of the times in chemistry, physics, and physical chemistry. But actually, you can use both. It depends on the problem you are encountering with. Okay, you will analyze if there's a given of internal energy, then you can apply this one. If there's a given of enthalpy, then you can apply the other one. So what is the most understandable and easy to understand situation of the problem, especially with regards to the given or data of the problem, then you can use either of these two, as long as these two are equations for the second law of thermodynamics. Okay. Okay, we have now the delta G Gibbs free energy relationship, and now I forget to tell you if there's a positive or spontaneous for delta G Gibbs free energy, and there's also positive which is non-spontaneous. We have also delta G is equal to 0, in which this is at equilibrium. Okay, at equilibrium. If the Gibbs free energy is equilibrium, so this will be the situation now. Delta G is equals to 0. Okay? Okay? So that is Gibbs free energy. Okay. Now we have also the relationship with the change in free energy, the standard and the not standard. So this is G. So this, guys, if we put degree at the top of the delta G, this is called the free energy change standard, or standard free energy change. Okay, again, this is the Gibbs free energy without the degree at the top, and this one is the free change of energy standard, or standard free energy. And then we have also the other one, which is G, okay, like this, not. So we have the change in free energy not in standard state. Okay, and so it's not in standard state. Okay, and this could be applicable in the free change energy, change of free energy not standard, can be applicable to pure substances, solid, liquid, and gases. So at 1 molar solution or concentration, or 1 atmosphere pressure and a temperature of 25 degrees Celsius or 298 Kelvin. So sometimes the problem will not specify that is the temperature and the pressure, but if given a chemical reaction and there's like this, free change energy, or energy free change, or free change of energy. Okay, we can rumble, but the precise is free change energy not in standard condition. Okay, change the ang iuna nimo. Okay, gives free energy. Okay, this is standard free change energy. Okay, and then standard change, standard free energy change. Okay, and this is free energy change not in standard, something like that. Energy change with siya ha. Again, gives free energy. Okay, and this is a standard change of free energy, not standard free energy. This one, because this is the word not. This is one having the conditions. Okay, the not, because it is only purely related to one pressure, and then at 25 degrees Celsius or 200 Kelvin. There's no other applicability. That's why it is not really applicable here. Okay, something like that. So the relationship also with Gibbs free energy. The Gibbs free energy and the standard free energy is just the same. Like this. Gibbs free, no, standard free energy change, like this, is less than 0. Okay, this one. This is also spontaneous. Okay, spontaneous. And then this is products favored. So this is products favored reaction, chemical reaction, and then your value of equilibrium constant will be uh, very large, or K will be very large. Equilibrium constant is very large. Okay, treating this in equilibrium in which your delta G or the delta S entropy is equal to 0, something like that, okay? So, standard, okay, standard free change energy. Standard change in free energy, sorry, is greater than 0, so this is equal to non-spontaneous. So this is reactance favored. So your K is less than, your K is small if the standard change of free energy is, okay, like that, is greater than 0. Okay, so we have a non-spontaneous, meaning reactance favored. Your K will be very less, okay, or less than 1, something like that, okay? And then if your Gibbs free energy is equals to 0, so therefore your K is just equals to 1. If your Gibbs free energy, this is a standard free change energy, or standard energy free change. Actually, you can interchange that one as long as there's a word of free. Okay, standard energy free change, or standard change of free energy. Depends, ha? Okay, that is equals to 0, and then your K is equals to 1. K is equilibrium constant. This means here, class, in the Gibbs standard, okay, change in free energy, this involves chemical reactions already because there's an equilibrium constant here. Okay, but in the G here, the Gibbs free energy doesn't really require a chemical reaction, but it can also have, but problems here are mixed, whether have the chemical reactions or not, something like that. But here, exclusive for the chemical reactions because of the word equilibrium constant. So, since this is equilibrium, let's treat it delta G is equals to 0 for here on. Okay? And the entropy also is treated constant, of course. Okay? Okay? Something like that. So, now we go to the other one, time check. Okay, time finished. So I'll be able to discuss also the signs of the Gibbs free energy. We're going back to the Gibbs free energy, not the standard change free energy, but the Gibbs free energy only, the signing, which are the energetically favored, and then energetically unfavorable, like this, okay? So something like that. Okay, so later. So thank you so much for watching this live streaming. I hope you gain a little bit of information about a mixture of physical chemistry, a little bit of physical chemistry, physics, and thermodynamics. Thank you so much, guys. This is again, I am a senior eternal voice, Engr.Sotero L, Nepomuceno Jr, and occupational safety health engineer. Thank you so much. Bye bye. God bless everybody.